Okay, so here we go. Now we're going to introduce the theorem, which is Gauss's method. And in this case here, this is what is true. It says if a linear system is changed to another linear system by one of these three operations. One, an equation is swapped with another equation in the system. Two, an equation is multiplied on both sides of the equation by a non-zero constant. And three, an equation is replaced by the sum of itself and the multiple of another equation in the system. Any one of those three operations, then the two systems, the one you started with and the resulting system after you made the operation, have the exact same set of solutions. Okay, now let's think about this as a let's do a proof of the first one. Okay, so if I have a system of equations, I'm only going to do the proof of the first one. The other two are similar. Okay, so if I have a system of equations, right? So if I have a system of equations, A1 oops, let's do 1, 1, 1, 2, right? And then we've got and then so on. We've got oops. Okay, so here's our system of equations. So now let's start with what needs to be true if we have a solution. So if we have a solution, S1 through S sub n, so if this n tuple is a solution, then what must be true? Well, this is a solution if and only if when we substitute S1 through Sn for all of these equations, all of these m equations, that they're all satisfied. They all give true statements. That means this one will give us true statement, and this one, and the next one, and the next one, and all of them. So we have a conjunction of true statements. Okay? So what does that mean? Well, it means that in a conjunction of statements, just like in logic, if we say A and B, right? So we say that that's true if and only if A and B are both true, right? So if we have A and B and C, then we would say that all the statement A and B and C are true if and only if all of them are true. So likewise, in a system of equations, we're going to say, hey, if we say that all of these statements, these mathematical statements must be true, which means they're connected by and statements. That means the order in which we organize those statements doesn't matter. We can move them around and the solution set still is the same, okay? Which is what we're set out to demonstrate here. So there's the proof in and of itself, right? And again, the other two are done similarly. Okay, that's it. So that's the Gaussian elimination method.